So last time we covered a couple of things that ranged from operating system services, and then we looked at the user operating system interface and we saw the different types. Then we also looked at system calls and saw the implementation of a system call. And then we also looked at the types of calls, and we ended up looking at system programs. So under the operating system services, we first of all noted that the operating system provides an environment for execution of programs and services to programs and users. Then we also saw a couple of functions that are useful to the user, and those included the user interface, the program execution, the input-output operations. Then we also looked at the file system manipulation, the communication, where processes exchange information on the same computer. And then we also talked about error detection. Then there were other functions that are provided by the operating system that offer better efficiency, and that included resource allocation, where there are many types of where you have many types of resources. Then you have CPU cycles, main memory, file storage, and so on. And then we also talked about the accounting, which keeps track of which user has how much and what kinds of computer resources. And then the protection and security, which is really to ensure control on the system and also protection from any external host. We also looked at a view of the operating system services, and we getting to the operating system interface, we actually looked at 3 of them. We looked at the command line interface, which is based on commands and uses different shells like bourne again shell, then the cone shell and bash and everything. Then we had also the graphical user interface, which is more user-friendly than the command line, and it uses icons. And then there was also the bash, which we looked at, which has a couple of tasks embedded therein, and it's loaded once and executes task by task until it completes. And then we also talked about the touchscreen interfaces, especially for mobile devices or smartphones. And we realized that they're quite different from the others because, you know, they have limited memory, and therefore they cannot execute just like the others. Then we also got to the system calls, and basically we said these are just programming interfaces to the services provided by the operating system. And we saw 3 common ones. That is the Win32 API for Windows, then the POSIX API for POSIX-based systems, which are mainly Unix, Linux, and then the Mac OS, and then the Java API for the Java virtual machine. And then we did say that when it comes to the implementation of a system call, it's typically a number that is associated with each call. And there's a system call interface, which maintains a table that is indexed according to these numbers. And we did say the caller needs to know nothing about how the call is implemented, but all they need to know is all they need to do is to obey the API and understand what the OS will do as a result of the call. And then that most of the operating system interface is hidden from the programmer API. And we also talked about system call parameter passing, which includes 3 general methods, where one of them is passing the parameters into registers, and then having parameters stored in a block or a table, and then having parameters placed or pushed onto the stack by the program. And then there's an option of block and stack methods to do, not to limit the number of length or parameters being passed. And yeah, we saw a couple of types of system calls, and we looked at the process control, file management, device management, information maintenance, communications, protection, and yeah, those were the ones. Then when it came to system programs, we said that they provide a convenient environment for program development and execution. And still, just like the system calls, they're also divided into the file manipulation, the status information, sometimes stored in a file modification, then the program language support, communications, background services, application programs, and the program loading and execution. So in a nutshell, that is what we looked at in the last lecture. And today we're going to look at processes. And under processes, we are going to look at under processes, we're going to look at the process concept, and then we shall look at process scheduling, then operations on processes, then we shall look at the interprocess communication, and hopefully we can also tackle the interprocess in shared memory systems, then the interprocess communication in message passing systems, and finally examples of interprocessor systems. That's if time allows. So let's jump in and look at the process concept. So the process concept is really about an operating system executing a variety of programs that run as a process. So we have a process, like we've always said, is a program in execution. And then we have multiple parts in a process image. And these include the program code, also called the text section. And then we have the current processor state, including program counter, the processor registers, including the stack pointer. Then we also have the stack contents, and these basically contain temporary data. And the temporary data includes stuff like the parameters. It includes stuff like the parameters, function parameters, address, return addresses, and local variables. Then we have the data section containing global variables. Then we have a heap containing memory dynamically allocated during runtime. And then there are other resources as open files, command line arguments, and then environmental values. So those are the multiple parts in a process. And a process, rather a program, is considered a passive entity that is stored on a disk. And it's basically an executable file. And then the process is what is active. So that means that more or less the process depends on the program, and the program becomes a process when the executable file is loaded into memory. So the execution of a program is generally started, if you are to consider a graphical user interface, it's started when you click on the icon of a particular, icon, or you enter a command on the command line. So we see that one program can actually be executed by several processes. And the example here, we have a compiler, you have a shell, and a browser. So you can open several shells. A shell is a program, okay? But then within that program, you can run several shells, which are the different processes. Or you open one browser, and then you have different tabs that are opened in this browser, okay? So the next thing is the process state. The process state, here we're talking about how the process changes, you know, from the time it's created up to the time it ends. You'll bear with me, I have a bit of cough, but bear with me. So the process, when it's newly created, that state is called new. And then after it's created, it goes on to what is referred to as the ready state. And for ready state, it's waiting to be assigned to the processor. And then after that, when it's assigned to a processor, whatever has been asked to be done will then be processed, and that is the running state. So the instructions are actually being executed, and then there is the waiting stage where the process is waiting for some event to occur and is not able to use the processor. So sometimes it could be that the processor is busy, or that process is actually waiting for an input or an output. So maybe if you're supposed to input something for it to continue, maybe when you open a browser, before you log in, you have that login page. So that process of the program, the browser program, will wait for you to input your login details before it can actually let you in to continue your browsing. And then finally, we have the termination, where the process has completed and it has to be ended. So we have this diagram to just talk about what we're saying. And generally, these edges are transitions, and they are labels. So these are the circular things are the edges we're talking about, but then they have labels. So we have the new, which is a new process, which is admitted, comes to ready, waiting to be executed. And then the scheduler will dispatch it. It gets running. And then sometimes it might be an interrupt. So when there's an interrupt, it will go back to the ready state, okay? And then it will be dispatched. And then finally, it gets terminated. Or as it's running, there might be an input-output event, just like we said, it is in the waiting state. So then someone has to input whatever output or input, whatever it's requesting for. And so it's in the waiting state, and until that input has been inserted, it does not continue. And then when it's input, then it completes and goes back to the ready state, and then into the running, and finally gets terminated. So that's the process state and how it happens. Now, during these processes as well, there's what is referred to as the process control block, and it's also referred to as the task control block. Now, this contains information that is associated with each process running in the operating system at that point. And so the processor state is taken care of, okay? So when you look at this processor block on the right, we have the processor state. So it's either wait, new, running, wait, or terminated. And then we have the processor number, okay? And then we have the program counter. And the program counter really is about the location of the instruction to execute next. Then we have the registers, which contain all the process-centric registers. And then we have the CPU scheduling information. This has the priorities or scheduling queue pointers. So what, depending on how the operating system is running, is it first in, last out, last in, first in, first out, last in, last out, first out, and so on, or is it round robin? So if it is round robin, there is a specific time that each process should run before, at least once before the cycle continues. So those are the priorities of the CPU scheduling information. And then there's the memory management information, which is handled in the memory limits. And here we know there's memory allocated to the process, and we shall talk more about it later. And then there's the accounting information, the kind of the CPU that's being used, especially if you have more than one, and then the clock time that has elapsed since the process started, and for how long it has to go on. Those are the time limits. And then finally, the input-output status information, where we have the input and output devices allocated to process and the list of open files. And so we have an example there of a process control block in Linux. It's represented by the C structure, task struct, part of which has the process ID. And so the process identifier is denoted by that PIDT underscore PIDT, ID rather, PID. Then long state, this one talks about the state of the process. And then the unsigned integer time slice, which shows the scheduling information. Then we have the struct, task struct, which is the process parent. And then we also have the child, okay, of the process. Like we're going to see, a process can have children, and then we'll see how they also work. And then we have also the list of open files, okay? And then, because remember, whatever file you open, it gets stored or uploaded in memory. And then, of course, that will affect the, how the memory works. So a list of open files is there. And if you want maybe the system to be better, you can close some of the files and have more memory so that you run your processes better. And then we have the struct struct, which is the address space of this process. So that is how the PCB is represented in Linux, and just for your information. Then we talk about scheduling. Scheduling has 3 levels. One is the long-term scheduling, then the medium term, and then the short term. Now for the long term, we're talking about having a decision being taken about which processes are admitted into the system. And usually it's just in batch systems. So remember when you talked about the different interfaces, we had the batch, where the batch was, you have a set of instructions that you load once, and then it will execute one after the other until it is done. And then we have the medium-term scheduling, and the decision is about which processes are memory resident. So what processes are in the memory and how are we going to deal with them? Which one will you work on first and stuff like that. And then the short-term scheduling, the decision is about which memory resident process gets the CPU next. So it's all about, trying to see which process gets to the CPU for processing. And so here, the short-term scheduler sometimes is also referred to as the process scheduler. Talking more about the process scheduler, the objective is really to maximize the CPU utilization, quickly switch processes into the CPU core. And this maintains the scheduling queues of processes. And therefore, it has 3 ways in which it does this. It has the ready queue, which sets all processes residing in main memory. And then it has the waiting queues, which are really to set processes waiting for an event. Remember when we talked about the process state, if it is in the waiting state and it's waiting for an input or output, Yeah, so that is also scheduled. And then we have the processes migrating among the various queues. So either it jumps into the ready state, goes to the running, into the waiting, and then it terminates. Then we have a new one coming in. It goes into the ready, goes into running, terminates, or goes into waiting, then back to ready, and so on. So the scheduler runs most frequently, so it must be very fast so as to handle all these different aspects. So we have a diagram there which shows the different transitions. So if you look at the left, we have the ready queue, which actually is responsible to send a task or process to the CPU for processing. So once it's sent to the CPU, it is worked on, and this arrow indicates that it's worked on and completed, and then it gets terminated. Then if it's not completed, then we have different things that happen. There is the input-output request, so the CPU works on it and then requires an input-output request, and then there is a waiting queue. And then when the input-output has been input, then it goes back to the ready queue. Then we have sometimes, like we said earlier, I did mention about time slots. So if the time for that particular process has actually ended, okay, if it is over, then that process will be taken back to the ready queue and will wait to be processed again. Then if that process requires a child process, then the child process will also be handled. And after it is handled, there has to be a queue for the child termination. So that once that child process has also ended, then it terminates and then goes back to the ready queue. And then it could be an interrupt. And when the interrupt is handled, still the process will go back to the ready queue into the CPU and then gets terminated. So we then go on to the CPU switch from process to process. And the CPU switch from process to process involves or could be referred to as the context switch. And it occurs when the CPU switches from one process to another. So from our diagram here, I'm sure you're able to see it. We have two processes, process P0 and process P1. Now, when process P0 starts executing, we realize that, okay, from this diagram, there's an interrupt or a system call. So what happens is when there is an interrupt happens while this process P1 is running, the operating system will save that state at which the interrupt happened, okay? And then it will continue in that state, okay? So as this process is actually being saved, then process P1 is loaded, okay, from the processor control block. It's loaded, and then it will now continue. Interrupt call still in process P1, then that process, the process P1, the current state will be saved. And then as it gets saved and everything, when it's completed, then the operating system will go back to process P0. Because the assumption is that when a system call happens here, it will load the other process that is in queue or that's been buffered. And then by the time it executes and completes, then the assumption is that process P0 has completed and it's also loaded again and executed to completion. And then once it's done also, then process P1 will be loaded again, and then everything will go on. And that's how there's going to be switching from one process to another. When one process is beginning to run and there's an interrupt, the operating system will allow that system call to be handled while it processes or operates on other processes that are queued up. So when the CPU switches to another process, it's important that the process that has been running that gets the interrupt, its current state is saved, okay, as in the old process, and then it's the one that will be loaded again for the new process via a context switch. So the context of a process is represented in the processor control block. So you'll get to know the previous state and then move on to the current state, and then the process will continue. So when during that time of switching, okay, the system actually does no useful work. And for the more complex the operating system and the processor control block, then the longer the context switching. And then also this context switching is time dependent on the hardware support. Some hardware tends to provide multiple sets of registers per CPU. So then you can store some of those things in those registers. And of course, with multiple registers, then you can have multiple contexts loaded at the same time. And of course, that has a bearing on the efficiency of the operating system. Now that brings us to the operations on processes. And we have two mechanisms that the system provides for, or that the system must provide for. And these are process creation and process termination. Just like we saw previously, the states, a process cannot start and run forever. It has to be created and it has to terminate. Because if it doesn't, okay, if it's created and doesn't terminate, that means it will keep using the resources forever. And that will mean, of course, there's a possibility of a deadlock, which we do not want to happen, or which the operating system looks out for and tries to stop. So talking about process creation, this is really about a parent process and a child process. So we have the parent process, which creates child processes, which in turn create other processes, forming a tree of processes. So generally, we have a process identified and managed via a process identifier. And we do have different resource sharing options during the during the process creation. And then we have execution options. So for the resource sharing options, we have circumstances where we have the parent and child sharing all resources. Then we could have the child sharing a subset of the parent resources. And then there could be a scenario where the parent and child share no resources. And then when it comes to the execution options, we have the parent and children executing concurrently, or we could have the parent waiting until the child terminates, then they can continue processing. So let me first stop this and share again so that we don't have the writings. Yeah, So we're saying we have those two options. Resource sharing options where the parent and child will share all resources. Children share the subset of their parents' resources, or both the child and the parent have independent resources, so they do not share. And for the execution, still we could have the child and parent executing concurrently, or the parent waiting until the child terminates. And then there's also the address space, which is normally a duplicate. The child has a duplicate of the parent, and then the child has a program loaded into it. And so looking at an example here of a child and a parent under Unix, if you remember, we said fork is really for creating a new process under Unix, and then execute is really about like running it. And this one is used after the fork to replace the process memory space with a new program. And then we have the parent process, which calls the wait for the child to terminate. So when we look at this diagram here, we create a new process, which is the parent, and then the parent generates a child, okay? And when the child executes, okay, it can go on to exit, and then it will wait to be terminated. And normally it's going to be the child, rather the parent, that actually terminates. So most times we are saying, rather certain times, we're saying that for the parent to continue or to execute, it needs to, rather the child has to depend on the parent. Though there are certain circumstances where the two do not share resources, or the parent has to wait for the child to terminate. So in this case, we realize that as the parent is waiting, okay, it allows the child process to execute, and it exits, then it waits, and then the parent will resume. So if there's any child process that actually is started, the parent will wait. So I could give an example of if you open a browser and then you open one tab, okay? Remember we said a program is passive and then a process is active. So the browser could be more like the program, the bigger program, or like the parent process, and then it has different tabs that are the child processes. So it keeps running, and if you close one of the tab, it ends and then waits until all the tabs are closed, okay? Then maybe you can later close it. But remember, the program or the bigger thing is normally passive and not active. So it's the different tabs that you open up that remain active. So that is about how the parent and child processes, the creation works. And then we have the process termination. And here, the process executes the last statement and then asks the operating system to delete it using the exit system call. And normally, it will return a status data from the child to parent. So sometimes, if the child is still running, of course, it will need to first execute and finish before it terminates. And then the process resources are also deallocated by the operating system as long as the child has terminated, and then the process also wants to terminate, rather the parent also wants to terminate. So the parent may terminate the execution of child processes based on any of these three. If the child exceeds the allocated resources, then the parent process will terminate it. And then if the task assigned to the child is no longer required, then still the parent will terminate that process. And then if the parent is exiting and the operating system does not allow the child to continue, if the parent terminates. So normally the child will depend on the parent, and therefore if the parent has been terminated by the operating system, subsequently, the child operating system, rather the child process, will also be terminated. So that is about the process creation and process termination. And more about the process termination, we are saying that some operating systems do not allow.
Excuse me, sir.
Yes.
So, like, I wanted more explanation on an example of a browser, where we have, for example, if the browser is the parent process and for example, the tabs are the child processes. There is an instance where you have one tab open, and when you close it, then the parent process, the browser also closes. Is that it? Do we have that scenario whereby the parent process will not run unless if we have a child process running? Is that instance existent?
Where you have the parent running without the child, or the child running without?
Where the parent will only run, if we have at least one child running. Does that instance exist?
No. Actually, I think if I get what you're trying to say is, if you close the tab, then the browser closes. But if you look at, for instance, what can I say? Okay, you can open a tab, okay, the browser rather, and the first tab will come, and you have not opened anything, but maybe it's the Google default page that comes. So if you remember where we started from, we have a program which is passive, and then the process which is active. So when you open that tab, it's more like you've opened the program. So if you open, maybe you go on to open up a specific URL, then you've started a process. And then if you maybe want to open several other tabs, then you're opening up other processes. So if you close all those tabs, okay, sometimes you may find that if it's only one tab open, you're literally closing the program. And so that's why it goes away. So a program can run without a child, especially if you just open it and it stays open, because it's passive until you really go back to it. So it's like you might open maybe a Word file and leave it there, or you open Microsoft Word, for instance, and then you're at that stage where it's a blank document, or you want to select a particular template. So it's more like that. It's there passive until you select what you want. Maybe you're opening up a file that you stored. And so it's the same thing with the browser. So you could have that browser there open, but without no specific URL, but it's there, and it remains passive until you maybe open up a specific URL, and then the process will begin. I hope that makes sense.
It does. Thank you, sir.
Right. Paul, anything? Okay, I see Paul unmuted. All right, so we're still talking about the process termination, and we're saying that some operating systems do not allow the child to exist if its parent has terminated. And indeed, it makes sense, because the child is dependent on the parent. But remember, we also said that there are three scenarios where you have the parent sharing resources, and then the child depending on the parent, and then where the parent and the child do not share resources. So if it's an operating system where the child and parent don't share resources, then the child can continue existing when the parent has actually terminated. But normally, when the parent terminates, the child automatically will also terminate. So it's more like a cascading kind of termination. All the children, grandchildren are terminated once the parent goes. And the termination is normally initiated by the operating system. And so we have the parent process, which may wait for termination of a child process by using the wait system call. And then it will return a status information with the help of the process ID of the terminated process. So if there's no parent waiting, as in it did not invoke the wait, then that process is considered a zombie, as it doesn't have, any parent. And then if the parent terminated without invoking the wait, then that process becomes an orphan. And of course, many times the operating system will just logically close it, because that is because that means it cannot continue moving, because some of its resources were actually handled by the parent. Then, excuse me, for the Android process, we have the hierarchy here that is important. And normally in the Android, the mobile operating systems often have to terminate processes to be able to reclaim the limited resources. Remember, we've been talking about the fact that resources on mobile systems or in the Android are really limited. And the reclaiming of system resources is dependent on, or is done from the most to the least important. And what happens is the least important will begin to be terminated, especially if resources are needed. So in the order of hierarchy, an Android system, we have the foreground process, especially things that you're working on at that point. Then we have the visible process, we have the service process, and then the background process and the empty processes. So if maybe the foreground process needs more resources, then the empty processes will begin to get terminated, the background processes, and some of the service processes that are actually idle, but not necessary. So that is how the Android works. And then we have the cooperating processes. But I would like us to have a break at this point, and then we will take it up from there and look at some of those things. All right, so let's take a 15 minutes break and then come back and look at the cooperating processes. All right. So let's continue. I hope now you're comfortable with the recording. So I was saying that cooperating processes are normally depend on each other, just like you have a friend you cooperate with. So also the processes are like that. And then we also have processes that are independent if neither can affect or be affected by the execution of another process. And we have reasons why certain processes cooperate. One of them is to share information, and then the other is to speed up a computation, and then also to increase on the modularity of an application. So by modularity, you're trying to break it down into different modules so that it can easily be processed faster. And that's the reason why sometimes you have child processes, because you have some other smaller process you want to run in the background so that the entire process can be made faster. So that's why some parent processes actually end up having child processes. So that's about the cooperating process. And it is also similar to what we talked about much earlier. We have an example here of a Chrome browser. And normally we have many web browsers that run as a single process, and many of them still do. But for Chrome, at least it has multiple processes, or it runs multiple processes with 3 different types of processes. One is the browser process, which manages the user interface, the disk and network input or output. So more like the program. And then we have the renderer process, which renders web pages. And this basically deals with HTML. And then we have the JavaScript. And this is a new renderer, which is that is open. So of course, now things are much better. But back in the day, if you try to go to a website which did not have JavaScript running, then you could end up actually failing to open up whatever page you're opening. But this is now much better. And the JavaScript is really to enhance security because it runs in a sandbox by restricting the disk and network input-output, minimizing the effects of security exploits. So here we have an example where you open up your browser there, and then you have different tabs that you open up. And so you have different web pages running, and that's the renderer process. And some of them probably require some kind of authentication, you know, if you have to log in maybe onto Moele or to access your email. Yeah, so then these other processes help you access. And then we have the plugin process for each type of plugin. So depending on the different plugins that you have, then we could continue. Rather, the browser will enable you to move on. Continuing on the inter-process communication, but under the cooperating processes, we're saying that we need the inter-process communication mechanism because it allows for exchange of data. And we have 2 models. That is the shared memory and then the message passing. Now, talking about cooperating processes under the shared memory inter-process communication, we are talking about an area of memory that is shared among the processes that wish to communicate. And so we have threads sharing memory, and that becomes easy. And a thread is referred to as a single sequential flow of execution of tasks of a process. So when you have a single sequential flow of execution of tasks, that could be a thread. So you have tasks to maybe a process running, but it has a sequence of tasks that have to be executed. So you could have a couple of threads running, and those are different like processes to complete something. And then this communication here in the shared memory is under control of the user processes and not the operating system. And that is why it's really under the inter-process communication. But of course, we know that overall, the operating system has the entire control over everything. Then processes do not have access to the same memory. So the operating system must provide a mechanism to allow them to create a shared memory region. So because these processes do not have access to the same memory, then the operating system comes in to provide a way in which to create that shared memory. And so when the processes share memory to communicate, that could be some kind of grave danger, of course, if the processes do. That is why the operating system provides a mechanism rather than allowing the processes to share the memory themselves. So by so doing, they end up synchronizing. Otherwise, they risk lots of bad problems. And then we have a problem that could arise out of that, which is the producer-consumer problem. And it's normally a pattern for these cooperating processes where the producer process produces information that is consumed by a consumer process. And we have two scenarios there. We have the unbounded buffer, which places no practical limit on the size of the buffer. And that's why it's called unbounded. And then we have the bounded buffer, which assumes that there is a fixed buffer size. So we have examples there. For instance, if you send a job to the printer is the consumer, and then the word processor is the producer. So sometimes, if maybe there are so many jobs that are coming to the printer, assume it's a network printer, and then probably you have a bounded buffer that assumes that there's a fixed buffer size. So if there's a lot being sent to the consumer here from the word processor, so many people are sending documents, the printer has a limited memory or a limited buffer. So of course, you realize that it will end up, kind of giving you a system call. The last people who sent that maybe printer can't print, it has run out of memory or something like that. So depending on what the problem could be, sometimes it's probably maybe many have sent jobs, but there is no paper in the printer, and therefore it can't print to remove and clear its memory. Or people have all sent their jobs within the same time. So the printer has to first print job by job until you finally get yours also printed. But of course, if you find that the buffer is full, then you'll be requested to send your job again because it cannot be sent. So that's the producer-consumer problem. And then when we talk about the IPC with the message passing, because the other one was for shared memory, here it's really about processes communicating and being able to synchronize their actions. So for the message system, we have processes communicate with each other without resorting to shared variables. So as opposed to the previous IPC setup of shared memory, here processes communicate with each other without resorting to shared variables. So they need to communicate, for instance, in this setup over here, the interprocess communication provides two operations. We have the send and receive. And normally the send requires a destination address. And here we're talking about, it could be a network and two hosts communicating. So that's why when you're sending, you require a destination address. Okay, so where are you sending this information and what's the message? And then the one receiving needs to know what's the source. Of course, this helps in terms of security and trying, of course, to see if the communication is going to continue, so that these are stored in the table, the IP table, so that the communication can be sustained. So this IPC facility provides these two operations, send and receive. And of course, the message size sometimes needs to be specified or just left open. So if the process P and Q wish to communicate, then of course there needs to be, first of all, an establishment of a communication link between them. And then the exchange of messages will then happen. This is typically what happens in TCP IP. And if you've done computer networks, if you did it last semester or doing it this semester, you will appreciate more of how it works. So an establishment of a communication link has to happen. So when you look at this, really, TCP is what happens here, and as opposed to UDP, because UDP is best effort. and it doesn't have to establish a link before it does the communication. But here, we're saying if processes P and Q wish to communicate, then they need to establish a communication link between themselves before they can actually communicate. And this said, there are some implementation issues that may arise, and these depend on how are the links established. Can a link be associated with more than two processes? And then how many links can they be between each pair of communicating processes? And what is the capacity of the link? Do links have buffering? Is the size of a message that the link can accommodate, is it fixed or variable, and so on and so forth? Is the link unidirectional or bidirectional? So these are critical questions that you need to ask yourself, especially when it comes to implementation issues. That's why sometimes if you're maybe communicating with, especially, okay, I'll give an example of Mwele. Sometimes you try to connect to it, but you fail. Maybe sometimes it's a capacity issue. So many students are actually accessing it at that time. And so you fail to access it, okay? And then at least here, it's not unidirectional, but it's bidirectional. Because unidirectional means you have to send, and after you've sent, you wait for the receipt, you wait for the response, and then you send again. But here you can send as much information before you actually get any response. And then sometimes, yeah, this issue of links, buffering, yeah, this okay might not be like specific to you, but if, for instance, maybe you have a VPN and you have to connect to maybe a company server and everything like that, you need to see whether, yeah, these links can be made in such a way that they're buffered, but all you need for instance, to access Mwele is just an internet connection. And so some of these things might not be taken care of, but these are some of the issues that you need to think about when it comes to implementation issues of these links. So the implementation of the communication link can both be physical and virtual or logical. And of course, when it comes to the physical, then things to do with shared memory are important, the hardware bus, and then the network. So yeah, as I was talking about Mwele previously, it had low capacity, and at least the guys who manage it, DICTs, did say that they had improved some of its hardware by increasing space, especially after it became very critical. And so there was a lot, also there was added memory and so on and so forth. Then of course, load balancing, if many students were accessing it, they had to, try and do everything right. And of course, the network. But still, there are challenges. Like they say, there's nothing, there will never be something that is enough. So despite, of course, the relatively good, rather high bandwidth, might not be also good enough, to provide the best service. But yeah, that is what life is about. You work within the scarce resources. Then for the logical, we have direct or indirect naming of links. And then there is also the ability, okay, this direct and indirect naming of links will depend on which processes are communicating, okay? So then they have to be identified. That is why we are saying direct or indirect naming of links. And that's done logically. The operating system does it, especially after you have, when you want to send a message, remember we have a destination address and the message. So that destination address, the OS can be able to, link up with that destination address, and then they name the links in a way that will show that, okay, this is the information that is moving. Because remember, even as the message goes, you need to say that I'm sending certain blocks. So the receiver the receiver machine or host should also know that I'm expecting 10 blocks. So before the 10 blocks arrive, it cannot say that I've received everything. And that's for TCP, but for UDP, it can just, I mean, since it's best effort, whatever comes through is what comes through, but it won't care whether everything has come through. And then when it comes to blocking or non-blocking transmission, yeah, depending on, remember the different functions of the OS, we talked about protection and security. So if something is not right, then that communication can be blocked. Then it could be symmetric or asymmetric. Send is non-blocking, but receiving is blocking. So if, for instance, like we said, when you're sending, you send a destination address. And then in the receive, there has to be the sender's address. So if you're seeing different things, one from the other, then of course, that's when the blocking comes in. And then there is that bit of the automatic or explicit buffering of a link. Sometimes, especially on, I'll give an example of these Zooms. If the network is not very good, yeah, someone speaking on the other side, maybe it could even be me. You realize either if it's your network or the one speaking, you hear, someone speaking slowly or in some kind of slow motion. That's a bit of buffering of the link. Or later on, you hear someone speaking so fast because something has been buffered. And so those are the things that happen there in the logical sense in terms of communication. Now, talking about direct communication, we're talking about processes being named, and this should be explicit. For instance, send to P, and that's the destination address, okay? You send a process, send a message to process P. But process P, you need to know where process P is, okay? And then receive a message from process Q. So in this case, if you're doing direct communication, it means process P is actually communicating process B, because remember we had here a destination address and a source address. So then you know that you're sending to P, and then Q will be like the source. So these names are bound at compilation time. And of course, once you compile, maybe if there's going to be direct communication happening between these two processes, at compile time is more like when you create the process. Remember where we started from, the process state. So you're creating this process, and then once the process has been terminated, then these names cease to happen. So they are bound at compile time, and when it's terminated, they are lost, and then you wait for a new process. And then when we talk about the properties of the communication link under direct communication, these links are established automatically, and they are associated with exactly one pair of communicating processes. So it can't be more than a single pair, but just two processes communicating. And then between those two processes communicating, there is exactly one link, and the link could either be unidirectional or bidirectional. And it's normally easy to implement, but cannot be used for client-server architectures. So direct communication will not work for you for client-server architecture. And of course, like we said, compiler time binding is very limiting. Then for the indirect communication, messages are sent directly and received from mailboxes, also referred to as ports. So if you look at, say, different services, for instance, if you want to pop up your mails, maybe you have different ports that you actually select. when you're setting up your Outlook. So if you have to pop your mails from Gmail or Yahoo or something like that, there are specific ports. So these are the mailboxes. In this case, you could have these ports specified, and each mailbox or port has a unique ID, and the processes can communicate only if they share a mailbox. So if it's an email process really, and you want to send maybe pop your mails from, say, maybe your student email or any other, you pop them to maybe Gmail or Yahoo or whatever, or maybe to an email client on your machine. Yeah, then you note that this is going to depend on sharing a mailbox. That's a port. And of course, you need, if you want to send a message, then you used to use the same command, send A, and here you're sending a message to mailbox A, and then you receive a message from mailbox A, because we said that these processes can communicate using a shared mailbox. So that's why we have the same address for both send and receive. And then the mailboxes might be owned and managed by the operating system or by the processes. So as opposed to the previous bit where we said processes, where we said actually it's operating system that determines, here in this case, the operating system can either manage the mailboxes or the processes. And when we talk about the processes, rather the properties of the communication links under indirect communication, the link is established only if the processes share a common mailbox. So if the link processes are not sharing the same mailbox, then the link will not be established. And also the link may be associated with many processes. So you could have a couple of processes using one mailbox, and then each pair of processes may share several communication links, as opposed to the direct where only it's a pair of processes that share a communication link. And then the link might still as well be unidirectional or bidirectional. Now, when it comes to the operations, what happens is a new email box, rather mailbox is created, which is a port, and it's for purposes of sending and receiving messages. And then after the communication is done, then the mailbox is destroyed. So this is already what we saw. So the primitives are defined as this, just like you write when you're beginning to write your codes, and you set or you call different classes that you will use. So it's the same thing. So you send to a particular mailbox, and you're sending a message to mailbox A, and then you receive a message from mailbox A, which is receive A and the message. So if a process, this is going to be the primitive if the process creates a mailbox it owns. And then if the process creates child processes, then they can access the process P creates a mailbox A, and then the process creates a child Q, and therefore Q can receive from or send to the mailbox A, because it is a child of process P. So that goes back to what we said over here, that each pair of processes may share several communication links, as well as the fact that a link may be associated with many processes. So you could have a parent process, like here, you have a parent P which created Q, but they're all using the same mailbox A. And so when it comes to mailbox sharing, we have process 1, process 2, and process 3 being able to share mailbox A, and then process 1 can send to process 2 and process 3. Process 2 and process 3 can receive. And so who gets the message? Here, of course, we are saying that if process 1 sends, then process 2 and process 3 will receive. Rather, yeah, will receive the message. And then if they have to communicate within each other, if there is a request from P1 to P2, then P2 will send back using the same mailbox to P1, and then the process will go on. Now, some of the solutions in this kind of arrangement are that you need to allow a link to be associated with at most 2 processes, as opposed to the indirect where it's just 2 processes linked to 1. And then you can allow only 1 process at a time to execute and receive an operation. So I think it's quite understandable in case, since they are sharing the same mailbox, in order to avoid chaos, there needs to be 1 process running at a time to request for information or to send or receive information. And then you need to allow the system to select arbitrarily the receiver. So in this case, where you're sending, P1 is sending to both P2 and P3. So the system should be able to choose who to receive arbitrarily, not without having to select. So the sender, of course, will be notified who the receiver was. And then if they are sending again, they know that so-and-so received, I need to send to another. So of course, there are many unanswered questions in terms of the lost messages, the faulty communications, process terminations due to some issues, of course, of network, and then the scrambled messages. So basically, these are some of the things that come with this communication. And then we now talk about the synchronization. And synchronization here is really about message passing, either blocking or being non-blocked. And when we talk about blocking, it's considered synchronous. And when you have a blocking send, the sender is blocked until the message is received. Okay, so until the number of blocks have actually arrived. For instance, if you're going to send a message which has 5 blocks, and so the sender says I'm sending, sender Q, P says I'm sending Q 5 block, a message which is 5 blocks. So sender P will first be blocked from sending until these 5 blocks that they are sending to Q have actually arrived. Then they can be allowed to now send again, because if you have to be sure of what has been sent, then you have to first wait for it to arrive at the destination before you can send any other information. And then blocking receive, the receiver is blocked until a message is available. So when, for instance, P wants to communicate to Q, it has to indicate I'm sending something to you. So Q wakes up and says, okay, send me. So, but before it receives that, okay, that maybe proposal that someone is going to send you something, then it remains blocked. And then for the non-blocking, which is considered asynchronous, the non-blocking send is purely about the message being continuous without waiting. And then the non-blocking receive, the receiver receives a valid message or a null message. So I could say that looking at these two, basically, this is really how the TCP IP works. And then this, if you are to borrow from the networking side, this is really how the UDP works. So this is best effort, but here you have to establish a connection before you actually send. And that's the reason why before you can send more information, you have to be sure that whatever you sent has arrived and has been received. Otherwise, then you have trouble. And of course, different combinations of this are available. If both send and receive are blocking, then of course, some kind of rendezvous. And then buffering I think we've heard about buffering. It's really about queuing of messages that are attached to the link. And it's implemented in 3 ways. There's one referred to as zero capacity. And here we have no messages that are queued on the link. And therefore the sender must wait for the receiver. And then the bounded capacity, we have a specified length of messages, okay? And so the sender must wait if the link is full. So if the sender wants to send and the link is full, they have to wait and then wait for it to release. It's more like the example I gave actually for the printer. If the printer memory is full and people are sending things to the printer for printing, they have to wait for the printer to actually empty its memory by printing whatever has been sent to it before, also accepting more information to be printed. And then we have the unbounded capacity, which is infinite. And of course, here, the sender never waits. But then this means you have a lot of resources. And so, yeah, these are the different ways of buffering. Then finally, we'll talk about the examples of the interprocessor systems. Okay, someone is saying you have another lecture. I'm winding up. This is the last slide. So the examples of the IPC systems, we have the match, and match is match communication is message-based, where we have each system calls that are messages, and then each task gets 2 ports at creation. And then we also have messages that are sent and received using the match message function. And then we have ports needed communication, and they are created via the match port allocate. And then we also have send and receive, which are flexible. For example, for options of if the mailbox is full, you have an option of waiting indefinitely. You have a wait at most a certain number of milliseconds, and then you can return immediately, or you can temporarily cache a message while the mailbox is full. And of course, you know that all these things keep happening. And of course, they've happened at a very fast rate. So this value of milliseconds, yeah, could be maybe about 100 milliseconds. And before you know it, the process has happened, and then you're able to receive and send. Yeah, so that is it for today. And I've seen some questions in the chat. Someone was saying that they have another lecture, but I think we had agreed that this lecture runs from 3 to 5. And so I remember I asked at the beginning and said it's okay to have it. So I don't know what is going on, because I think, especially I think for the software engineering class, I think they said the lecturer said he'll be teaching on Friday. So maybe the person who asked is not aware of this. So I shouldn't expect anything like that. So this lecture runs from 3 to 5. So please take note of that. And then someone is anxious for a test. I will communicate. I'll communicate when the first test is due. And then, of course, the recordings, I normally put them up on Mwele. The one for last lecture delayed because of some issue on Mwele. So I've been trying to fix the issue. Rather, I requested for help from the guys concerned, and yeah, they came through this morning with the solution. And if you checked, you probably have seen the link for those, the link for the recording, and this one will also be put there as well. All right, Maria, your hand is up.
Good afternoon, sir.
Good afternoon.
I'm requesting for the course code because
The course
the
code.
Yes.
Who knows the course code? Kindly type it in chat. Liazi, Marvin, type the course code in chat for Maria. So that's the code, Maria. Any other concern?
You are going to work at tests minor.
Adeti. Adeti, what are you saying? What's wrong with the test?